Welcome to this video in which we will still be talking about interpolation using splines, but this time we will be using cubic splines to do the interpolation. So because of splines, we will still be looking at individual intervals, but now, as the name cubic splines implies, we will be using third-order polynomials in each interval. So let's look directly at the standard form for the interval that goes from xi to the neighboring point xi plus 1. So we will have a function f for the interval I that is a cubic polynomial. So that is a sub I times x cubed plus b sub I times x squared plus c sub I times x plus a di. And that function, that cubic polynomial, is valid in this interval where x is between xi and xi plus 1. Now, we have a total of n minus 1 intervals, and if we look at this cubic polynomial, the number of unknowns for each one of these intervals is 4. So we have a total of 4n minus 4 unknowns. Each one of the n minus 1 intervals has a cubic polynomial with each 4 unknowns. So now we have to come up with conditions in order to calculate these individual coefficients ai, bi, ci, and di. So what are they? Well, first of all, this polynomial, the fi of x, must pass through the interval endpoints data points, right? Because it's interpolation. So when I plug in a data point into my interpolation polynomial, I want to get back the measured data yi. So f of I must pass through xi, yi, and xi plus 1, yi plus 1. So that means if I plug in xi into the polynomial, as shown here, I must get back equal to yi. And the same applies to the other endpoint, xi plus 1, yi plus 1. If x is equal to xi plus 1 in the polynomial, that should be equal to yi plus 1. Okay, so the total number of equations that I have just determined is 2 equations per n minus 1 intervals. So a total of 2n minus 2 equations to determine the 4n minus 4 unknowns, so not enough equations. So what else can I say? Well, at interior knots, those are these blue dots, the first derivative of adjacent polynomials shall be equal to each other. So I have a smooth slope when I transition from one interval to the neighboring interval. So at knot I, that means that the first derivative of the function fi and fi minus 1 has to be equal at the knot. So if I calculate the first derivative of the cubic polynomial, I get 3a x squared plus 2bx plus c. If I plug in the point xi into this formula for the left subinterval, that has to be equal to the derivative evaluated from the right subinterval at the point xi. So that gives me an additional equation for every knot, so for every interior point. And since there are a total of n minus 2 knots in the data set, I have another n minus 2 equations. Now those were the conditions that we had as well for the quadratic polynomial. So over the quadratic spline. So what's new now for the cubic spline is that we can also guarantee that the second derivative of adjacent polynomials is equal at interior knots. So at knot I have that the second derivative, which is 6ax plus 2b, is the same whether I evaluate it from the left interval I minus 1 or the right interval I, that both meet at the grid point xi. So that means that 6ai minus 1 xi plus 2bi minus 1 is equal to the same thing evaluated for the right polynomial, so 6ai xi plus 2bi. So that gives me another n minus 2 equations, one equation at every knot. So let's take stock. How many equations do I have now? Well, I got the 2n minus 2, I got another n minus 2, and another n minus 2 equations. So that if I add this all up, gives me a total of 4n minus 6 equations. Well, 4n minus 6 equations, close, but not good enough. I'm missing 2 equations to determine my 4n minus 4 unknowns. So where do I get these additional two equations from? Well, that's where the so-called natural cubic spline comes in. So the condition for a natural cubic spline says that the second derivative from the first interval at the very first data point and the second derivative of the last subinterval, n-1, at the very last data point, xn, both of them are supposed to be 0 at those endpoints. So those are, if I use the definition for f double prime, that gives me 6a1 x1 plus 2b1 has to be equal to 0, and 6an minus 1 times xn plus 2bn minus 1. That has to be equal to 0 as well. And those are my additional two equations that I need. And now I have 4n minus 4 equations for the 4n minus 4 unknowns that define my cubic spline. Okay, so here is now the summary of all the equations that define the coefficients for my cubic spline. Now, in an interior interval, right, every interval from 2 to the last one, n minus 1, I have the total of 4 equations, namely that the polynomial has to go through the endpoints and that the first and the second derivative is continuous at the left point. But I can't write all 4 conditions for the very first subinterval because there is nothing to the left of the very first subinterval. So I only have for the first interval I equal to 1, I have the condition that the polynomial from the first subinterval has to go through the endpoints. But I would like to have 4 equations there as well. And I'm just taking the 2 equations from the natural cubic spline condition and add them to the 2 equations that are naturally there for the first subinterval to turn that again into 4 equations that I just count for the first interval. So therefore, every subinterval will now have these 4 equations as shown associated with them. So if we look at these equations, fortunately, those are all linear equations with respect to the unknowns, the ai, bi, ci, and di. So it's a 4n minus 4 by 4n minus 4 linear systems for the unknowns that we have to solve numerically typically. And how do we do this? Well, using my Gauss-Jordan with partial pivoting. Okay, so now how would we code this? And we will touch upon how to code this in detail in the recitation. But here are some comments of how to address coding. Basically, it's follow the comments from the quadratic spline. Modifying some things. For one, there are now 4 unknowns per interval instead of the 3 from the quadratic spline. And there are also 4 equations per interval instead of the 3 from the quadratic spline. The row and the column number equations for an interval I have to take this into account, right? That I have 4 equations instead of 3 equations, 4 unknowns instead of 3 unknowns. But once you've taken that into account, then you set up the matrix A and the right-hand side vector, very similar to what we did for quadratic splines. It's just a larger system that we then solve again using our Gauss-Jordan technique. Thank you for watching.